This is lecture number 2 in this series on nonlinear systems. In the last lecture, we studied why we use a nonlinear system, why we study a nonlinear system, and what are the various properties of a nonlinear system. What we'll be doing now is through various examples, we'll be trying to look at the difference between a linear and a nonlinear system, and also we'll see how we can model a nonlinear system and see how its analysis is different from that of a linear system. So let's take various examples. So the first example I want to we'll be looking at is, let's take an example of a system having governed by a differential equation x dot plus x equal to u, that's dx by dt plus x is equal to u. So this is a first order differential equation, ordinary differential equation, and if you know about this system, since it's only first order, so that means there's only one state variable. So if we can represent this system in a state variable form, we can put this in a state variable form like this: x dot equal to minus 1 x plus 1 times u. Fine. So there are only one elements in each A and B matrices, and since A is equal to A matrix is minus 1, the eigenvalue is also minus 1. It's safe to say that this system, this differential equation represents a stable linear system. Fine. So this here is our linear system. Now for this linear system, we know with linear systems, for the behavior of the system, for say for example a unit step input of 1, the output will have a certain transient period and finally settle at this place, so where x dot is equal to 0. For this very case, x will be equal to u. That means the state variable x is settling finally at this depending upon the input of the system. If we increase the input of the system, what will happen is the output will also change and settle at the new reference value. Fine. So looking at these two inputs, as you increase the input, the settling time of the system increases. Now we'll make this system non-linear, and how we can make the system non-linear is by instead of you having x dot plus x equal to 0, we can have x dot plus x square equal to 0, and instead of writing x square directly, I'll write it x into mod of x is equal to 0. So this now here represents a non-linear equation, non-linear differential equation. This x dot plus x square equal to 0 is actually is the governing equation of an underwater vehicle system, representing the drag of the system. While we apply the thrust u, x square represents the drag velocity. X represents the drag velocity. Fine. So this is a nonlinear differential equation, and we want to see how the system behaves differently in case of a nonlinear system. Now let's again say we are applying an input of u. For this case, what we'll be doing is 1 will be applying an input of u. So we are applying an input of u that lasts for 5 seconds, and the magnitude of this input is 1. Fine. And secondly, then we'll be applying an input of we'll then be applying input u having a magnitude 10 lasting for 5 seconds. So what will be the difference in the output of this output represented by this nonlinear differential equation is that what you will see, the output will be like the system will first rise as is happens, then it will settle at a certain point, and since then we are removing the input u at t equal to 5 seconds. Fine. So at t equal to 5 seconds the input u becomes 0, so that means output will also decrease. The settling time of upwards, when we see this settling time is much quicker as compared to when it settles down in the negative half after removal of the input. So once we apply the input, once we apply a positive unit step input to this nonlinear system, the settling time of this system is achieved faster as compared to the settling time when we actually remove the input. So that is something we see in case of linear behavior as well. But what we do not see in case of linear systems is what will happen when you apply input of magnitude 10. So with linear systems, the settling time actually increases as you increase the input of the system. But in this case, what will happen is the settling time will become like this. This will be the new behavior of the system for for a unit step u equal to 10, and this will be the behavior of the system for u equal to 1. Fine. So this example you can has been taken from Slotkin-Lee nonlinear system analysis. So what we do here is we are applying two different inputs to a nonlinear system, x dot plus x square equal to u. In the first case, for u equal to 1, what you can see is for u equal to 1 and x dot equal to 0, you can say x equal to under root of 1. That means velocity of the system is under root of 1. But for u equal to 10, x dot equal to 0, x will be under root of 10. That's like 3.14 something. So since the velocity increases, the settling time decreases. So with a linear system, u does not increasing the u does not decrease the settling time, but it takes for the system to achieve the response in a longer it takes a longer time to achieve this output response. But in a nonlinear system, what you are seeing is this property has already changed. Fine. So this is something that you will see in nonlinear systems. These things will vary. Fine. This is not actually going to be constant throughout, that with all nonlinear systems with increasing u settling time will decrease. That's not going to happen. But here you can see with linear systems the behavior is always like this. For a stable linear system, for a stable LTI system, you'll see that increasing u increases the settling time, but with a nonlinear system you'll see that increasing the input may decrease the settling time, may increase the settling time. It can make the system unstable. Fine. So this is how you can this is one example where we are showing that how non-linear system and a linear system dynamics, they are basically different. Now it's like another example, that of a simple pendulum, and we'll try to model this equation. So this is a simple pendulum having a mass m, length g, length L, and pulled by gravity, having gravity G. Now this pendulum is here actually representing only 1 degree of freedom, wherein this theta is varying as the m moves. This theta is actually varying. Fine. We can have different types of pendulums. We can have an inverted pendulum. We can have a pendulum with 2 degrees of freedom like this. We can have a system having 2 joints. So you'll have 1 theta, you'll have theta 1, you'll have theta 2. So for this very system, theta 1, theta 2, at 2 different points, the pendulum is having 2 joints, and therefore having angular position is changing into different there are 2 independently varying angular positions, theta 1 and theta 2. So therefore it has a 2 degree of, it's a second, as far as the degree of freedom is concerned, for the second case it is having it is 2, whereas for this simple pendulum case that we have taken, the degree of freedom is only 1. There is only one independently varying state variable angular position, that is theta. So you can have you can have different pendulums. You can have an inverted pendulum, you can have rotary pendulum, you can have a Furuta pendulum. So there are there, depending upon different degrees of freedom, depending upon in what plane the mass m is actually, the angular position is actually changing, in what plane of rotation is m moving. So we can have different types of pendulums, and what this pendulum is here actually, it represents one of the most important examples that has been studied in control systems in the nonlinear domain as well as in linear domain, and its properties have been extended to various applications, that in rocket propulsion, in aeroplane propulsion, in robotics, in you can see in we have medical surgeries. So this example, the dynamics of a simple pendulum and its all forms have been extended to various applications, and this therefore represents a very important example. Now we are taking a simple pendulum to start with. As I said to you, we will be in this, the degree of freedom for this simple pendulum is only 1, and its state variables, we can represent the state variables as x1 equal to theta and x2 is equal to theta dot. So we'll also be taking care of how this angular velocity of this system is basically changing. Fine, but this angular velocity is actually not an independent variable, it depends upon theta, so it cannot be taken as a degree of freedom. The degree of freedom here only represents the sole independent variable, that is theta. That does not depend upon any that actually uh, represents the system dynamics. So using a state space model, we'll try to model the system. For finding out the differential equation that actually governs the motion of the system, what we have been using is the Euler-Lagrange equation. So this equation is used for finding out the nonlinear dynamic equations, differential equations of various nonlinear systems. The Euler-Lagrange equation is given as d by dt of dou L by dou theta minus dou L by dou theta equal to the force, in this case that is torque. So this equation is actually represents a system of second order differential equations. So wherever ordinary differential equations, so we having so using these equations, so wherever the we'll be using second order differential equations, we can use the Euler-Lagrange equation, or even extend that to fourth order differential equations, and so on. And as far as this is theta dot here, fine. As far as this L is concerned, it is known as the Lagrangian of the system. And L is given by kinetic energy of the system minus potential energy of the system. So using Euler-Lagrangian equation, we will be able to find out the differential equations governing the motion, governing the dynamics of various nonlinear systems. Dou d by dt of dou L by dou theta dot minus dou L by dou theta is equal to tau, where in this particular case, what we are assuming is that, say for example, a motor or an actuator has been placed here that is actually causing this mass m to move from here to back to here. Fine. So it's showing a pendular motion due to an actuator that is placed here. So the motor that's actually rotating will have generated torque, and that will act as an input to the system. That torque be equal to tau. Again, depending upon the application of the pendulum to particular example that we might be trying to fit it in, we can have the thrust being applied directly on the mass in certain cases. Fine. So say for example, you take an example of a swing, a simple swing in a park. What happens there is that the thrust is applied directly at this particular point. Fine. So this is our example, but in this case we are having an actuator here and applying that to a body of mass m, and we want to see how this theta is varying in this field. we'll be trying to find out the state space model of the system. So for that we'll be using the Euler-Lagrange equation. Now therefore for this particular system, what will be L? The kinetic energy of the system. Kinetic energy is given by half of mv square, where v here is actually going to be represented in terms of the angular velocity phi and through the radius of the system. So we'll say it is 1/2 of r 1/2 of mv square. Instead of v we have r omega, so r square omega square, r is here L square, omega square, that is actually d theta by dt. So you can say theta dot square. 1/2 of mv square, v is r omega, r is L, and omega is d theta by dt, minus mg h, the potential energy, and L will be given here by, the height will be given by L1 minus cos theta. So depending upon the position of the system, h will be L1 minus cos theta. Now this is our equation number 2. This is our equation number 1. Fine, so we have to put L here, so that means we have to actually differentiate L with respect to theta dot and L with respect to theta, and then also differentiate this with respect to d by dt, the first term. So put L here in this equation, so that means we'll be getting d by dt of dou by dou theta dot of L, where L is 1/2 of ml square theta dot square minus mgl 1 minus cos theta, and minus dou L by dou theta of L, that is 1/2 of ml square theta dot square minus mgl 1 minus cos theta is equal to tau, the thrust input U. So differentiating this with respect to theta dot, so this is a partial differentiation. So that means this becomes d by dt of tau 1/2 of ml square into differentiation of theta dot square, that becomes 2 theta dot, so 2 and 2 will go, so this becomes ml square theta dot only minus mgl 1 minus cos theta, so differentiation of that with respect to theta dot will be 0, so this portion finishes, minus 1/2 of ml square theta dot square, differentiation of that with respect to partial differentiation of that with respect to theta is 0, minus mgl 1 is 0, cos theta is minus sine, so this becomes actually minus mgl minus sine theta, so this becomes actually plus sine theta is equal to tau. So d by dt of ml square is constant, so d by dt of this is d theta by dt, d by dt of d theta by dt means d square theta by dt square, so that means this is second order differential equation. Now ml square theta double dot plus mgl sine theta is equal to tau. So this here represents a second order time invariant ordinary differential equation. So this also represents the motion of the simple pendulum, ml square theta double dot plus mgl sine theta equal to tau. Now since we know what we have assumed here is that x1 is equal to theta and x2 equal to theta dot, so therefore x1 dot is equal to, you can say that is directly x2, and x2 dot is equal to what? X2 dot is actually this term, so x2 dot will be equal to tau minus mgl sine x1 divided by ml square. Minus mgl sine theta minus mgl sine theta plus tau divided by ml square. Fine. So if tau is equal to u, x1 and x2, so therefore x1 dot x2 dot is equal to 0, 1 minus mgl by ml square, and it's 0 here. What else we have here? We have here x1 x2, so this is actually sine of this term. Fine. So we cannot actually write it exactly like this. This I'm just showing for illustration. 0 and 1 by ml square of tau. Fine. So we can actually put x1 dot x dot and x2 dot in this particular form. So you cannot actually separate sine and x1s. You cannot put them like this in two different matrices. I just did this for illustration. And also this m and m actually here goes l, and l goes, this is actually minus g by l here only. So x1 dot is equal to x2 and x2 dot is equal to minus g by l sine of x1 plus tau by ml square. So exactly we cannot put it in the matrix form. I would actually like to point that out. This representation is not exactly accurate, but x1 dot is equal to x2 and x2 dot is equal to this thing. So this here represents your state space model of your non-linear system, of that of an inverted pendulum, and you can actually say x dot is equal to f of x1 comma x2 plus g of x1 comma x2 comma u. So your state space form of a nonlinear system can be put like this: f of x1 x2 plus g of x1 x2 u, where f and g represent the functions that relate x dot with x1 x2 and u. So this is how we can derive the state space model of a nonlinear system. Now exactly we cannot find out the eigenvalues directly of the system without linearizing this system. So this state space model in the matrix form cannot be written because we cannot actually separate the sign and x1 and put them in two different columns. And for putting this x1 and x2 in a matrix form, this here does represent a set of two first order differential equations that we have obtained from a one second order differential equation. So we have done some thing that we actually do in state space modeling, but we cannot put it in a matrix form as of yet because sign of x1 cannot be split like that. But to do that, we have to linearize the system. So we are not actually going to do exactly the linearization right now because that will be a topic for later. But I just wanted to point it out how we can model a nonlinear system, and for that we have taken an example of a simple pendulum. Now here here we'll try to find out the equilibrium points of the system. So equilibrium points, as I said to you in the last session, is actually a set of points that represent these are a set of points where x dot x becomes equal to 0. That means without any external disturbance, the system will tend to remain in this state forever at this very particular point if there is actually no external disturbance. So for our particular case where x1 dot is equal to x2, and x2 dot is equal to minus g by L sine of x1 plus tau by ml square. If you put them equal to 0, so x2 will be equal to 0 always, but as far as this quantity goes, sine of x1 will be equal to 0 at a number of points where x1 will be x1 equal to 0, x1 equal to pi, x1 equal to 3 pi, in short is equal to n pi. So what will be the equilibrium points? So the equilibrium points therefore will be zero comma 0, pi comma 0, 3 pi comma 0, n pi n plus, actually where n represents if 2n plus 1, sorry, 2n plus 1 comma 0, where 2n plus 1 represents all odd numbers, 5 pi, 7 pi, 9 pi, so on. So there are not one equilibrium points, there are not two equilibrium points, there are 2n plus 1 equilibrium points for this particular case. So this was another thing that we do not see with a linear system. With a linear system, we only have one equilibrium point, a unique equilibrium point, where x1 dot is equal to 0 and x2 dot is equal to 0, x3 dot equal to 0. So what does that mean? Since these are all first order differential equations in in a linear domain, x1 dot will only have one root, x2 dot will have only one root, x3 dot will only have one root. So x1 dot will be unique, x2 dot, the solution of x1 dot equal to 0 will be unique, the solution of x2 dot equal to 0 will be unique, solution of x3 dot equal to 0 will be unique. So even if there are n states in the system, solution of all those n independent first order differential equations will be unique, and therefore you will have a single equilibrium point wherever for a linear differential equation. But for a nonlinear differential equation, you do not have that case, because we have terms like sine of x1 on the right side, x square on the right side, x cube on the right side. So solution of these equations will have more than one roots. So therefore the equivalent points will also be multiple. So now, figuring out whether the system is stable or not, you will have to find out stability at 0, 0. You'll have to find out stability at pi, 0. You'll have to find out the stability at 3 pi, 0. So this is how, again, a nonlinear system is different from that of a linear system. So we have taken some examples today just to illustrate the behavior of nonlinear systems, how to model nonlinear systems, how their behavior is different from that of linear systems. So in the next session, we'll now be looking at some commonly occurring nonlinearities in nature. That's all for this session.